Or you can. I don't know.
Because recording has started. So you can start now.
Rajesh Bhaiya, please say something. Actually,
Yeah,
I'm
recording has started. Can you
recording.
listen me?
So I am not listening. Voice is not clear to me, and Mithunda's voice is also not.
Okay.
So just
Uh,
yeah, okay, okay. Let us start.
so Muna,
Yeah,
so you will be finishing by 4:45, no?
yeah.
Okay. Yeah,
So you
because
have to go.
I have clicked the button recording.
Okay, okay.
Yeah.
4:45. Okay, I will try.
Yeah, yeah.
Okay, so welcome back to lecture 18 on Riemannian symmetric space. So last lecture we saw the definition of a symmetric space, Riemannian symmetric space. So this is the definition. Let M be a Riemannian manifold with dimension of M is greater than or equal to 1. Then M is called a Riemannian symmetric space, or simply a symmetric space if for each p belongs to M there exists an isometry SP from M to M, so that SPP is equal to P and DSPP is equal to minus of identity. Okay. So that is to say that for each point P there exists an geodesic inversion at the point P. Okay. So using that we have first proved the proposition like this. Okay. So let M be a Riemannian symmetric space. Then M is complete. We have proved that. So how we have proved that? Let us recall a little bit. So first, actually, we since it is equivalent to say that showing completeness is equivalent to showing that M is geodesically complete. So let gamma be a maximal geodesic, so that domain of gamma is really not equal to R. So then what I do, we have chosen a point P where so that P asymmetrically divides this geodesic gamma. Then actually if you apply this SP to this geodesic gamma, so if this is gamma, then SP actually what SP does, SP simply flips the geodesic about P. Okay, so SP gamma will be uh, if I will apply that, that will be some different thing. So essentially it will flip the geodesic, so it will continue in this direction, and something like this will happen. And then we got an extension of this geodesic gamma, and that contradicts the maximality of the geodesic gamma, and that shows that M is geodesically complete, therefore M is complete. Okay, so today actually we are going to see some examples of this Riemannian symmetric space. Before that, we need to really prove a simple proposition. Let us prove that, and that proposition will be useful for us very later. Proposition. So let M be a Riemannian manifold so that this Im acts transitively on M. Actually, by Riemannian manifold, I will always assume that dimension of M is greater than or equal to 1. This I explained last time, so it is really perfectly makes sense to take this condition. And let P belongs to M so that there exists an isometry SP belongs to M with SPP is equal to P and DSP P is equal to minus identity. Okay. It says that there exists an geodesic inversion at the point P, then M is a Riemannian symmetric space. Okay. So we need to really prove this thing. So what it says that if M is a Riemannian manifold, so that isometric group acts tangentially on M, then if for some point P belongs to M, there exists a geodesic inversion, then you will be able to define some geodesic inversion at every point, and therefore M is a Riemannian symmetric space. Okay, so the proof idea is very simple. See, the thing is, since this IM acts, let Q. Okay, so idea is, let us discuss. So let Q belongs to M. Okay, since this isometry group acts tangentially on M, so this implies Q is equal to really G dot P. So we want to define an geodesic inversion at the point Q, SQ, and this is same thing as sub G dot P. We are given a geodesic inversion at the point P, we have to use that. So if you think for a moment, then SZ G dot P, the natural candidate for SZ G dot P is really G composition SP G inverse. Okay. Now if you look at this S of G dot P at the point G dot P, then this will be actually G dot SP G inverse and G dot P. So that will be G dot SP, G inverse G dot P is really P, and this is G dot P. And similarly, you can check that derivative of SGP is really minus of identity at the point GP. This is the thing. But however, there is an issue here. So you can write Q. Q may have two different representations like Q is equal to G dot P or H dot P. So if one also can define this SQ like S of H dot P, this is really H SP is H inverse, and so there is a problem in the well-definedness of this definition. There are two expressions for SQ we are getting, so we have to show that these two things are same. Okay, let us first fix this thing. So okay, so let us say let let K is equal to this thing, G belongs to IM, so that GP is equal to P, and this is what stabilizer of P inside the group IM. Okay, now so let K belongs to K. Composition of isometry is an isometry K SP K inverse. This belongs to IM. Okay. Now this K SP K inverse at the point P, since everything here fixes this P, so this will be P. Now I take the DK SP K inverse at the point P. This is really DKP and DSP P and DK inverse at the point P. Now I am given that this term is DSPP is minus identity. So if I will put that, that will get minus of DKP and DK inverse of P. Now DKP, K and K inverse are inverse of each other. So this will I get, this will be a minus of identity. So look at this expression that KXP K inverse P is equal to P and D of that map is really minus identity. Hence by rigidity of isometries, this by rigidity of isometry, so we will get this K SP K inverse is equal to SP. I call this as 1. So this sort of so let G dot P is equal to really H dot P. That means H is equal to GK for some K belongs to this K. Now this is H of SP H inverse, same thing as G of K, okay, SP, and this is really K inverse. So that is really G K SP K inverse, and Sorry, this is G inverse, not G inverse. And KSP, K inverse is your SP, so this is really uh, GSP, G inverse. Hence, SG dot P is equal to really GSP, G inverse is well defined. Now, what I want to do, okay, so what is, as I've shown that SP of G dot P at G dot P is really G SP, G inverse, G dot P. So this is G of SP P and this is G dot P. Now ds gp at G dot P, this is the dg, dsp, dg inverse, and I put here first G dot P and G inverse G dot P is P, this is P. Now I am given that DSPP is minus identity. So this is minus identity. So this is really minus of DG, DG inverse P, and G is inverse are inverses of these both minus identity. So hence SG dot P is a geodesic inversion at G dot P. Now as I am transitively on M, so M is an RSS. M is a Riemannian symmetric space. So this proves the fact that the proposition. Now we want to really give an example of symmetric spaces. Okay, so what actually symmetric spaces actually?
No, Muna, what was the conclusion?
Confusion or conclusion?
Conclusion.
M is a Riemannian symmetric space because G dot, as you vary G dot P will vary
No,
throughout.
what was your assumption? What was your assumption?
Assumption is really M be a Riemannian manifold so that I am acts transitively on M, or let P belongs to M be so that there exists SP belongs to IM with SPP is equal to P, DSPP is equal to minus identity. That means for a single point P, I have an geodesic inversion, and I am really proving that geodesic inversion exists for every
All
other
points.
point.
Okay, fine.
Okay. So the thing is, SP actually, SP in a Riemannian symmetric space, SP is simply a geodesic inversion. If you take P, it will simply just flip this geodesic to this part, this geodesic to this part, and that say that if you have in a Riemannian manifold, if you know geodesics, and then it is really, if you know that it is a Riemannian symmetric space, it is easier to write so-called the SP, because let us see some examples. So first example is your Rn. I want to really specify this SP. So let us P belongs to Rn and fix a direction. Okay, and geodesics will be of this form P plus TB. So suppose V is a direction and this is my geodesic point P plus TB. Okay, so this is my point. So simply SP since takes flips the things, flips the geodesic. So P plus TB will go to other direction, that will be P minus TB. Okay. So since it is very easy to see that, so SP of P plus TB is simply will be P minus TB. And if you really write P plus TB is equal to W, okay, so this implies TB will be what, W minus P. So SPW is really P TB is equal to W minus P This is really minus of W plus 2P. This is the description of SP, and this is really clearly, this is a so-called affine map, and therefore ISP belongs to clearly this is I of Rn, and so SP of P is really what minus P plus 2P is P, and DSP P is really minus identity. So you can directly also, we here know the explicit the isometric group of Rn. For that, we can easily really conclude that SP belongs to Rn. If you do not know the knowledge of isometric group, you can directly verify that. This is a fairly simple example, perhaps the simplest example. Okay. So now let us see the for B. This is the Sn minus 1. Yes, so let P comma X belongs to Sn minus 1. So we want to determine SPX. For sphere case also we know the geodesics. These geodesics are great circle, and I also told you if P and X are two different points, so there exists a circle which really contains P and X. So let us draw a picture. So this is my point say circle. This is my origin, and suppose this is my point P.
Numa,
Yes, sir.
how could you draw this circle?
Oh, there is something, some tool is here.
Okay.
Actually, this
I
is
will
the
just press it for some time. Just keep it there, so it will automatically turn into a circle.
actually, sir, it is a paid app, so you expect
No, Muna, you
that.
don't need that. On
Okay, never
iCard, it
mind.
is
Go
there.
on.
Okay, this is P. Okay, so this is my point P, and suppose this is my point X. Okay, so this is if you go in this direction, this is we are really going there along a geodesic, and you reach PX. Since SP is the geodesic inversion, SPX will be something like this. This will be my point SPX. Okay, by your simple argument. Now we have to somehow find this X SPX. What is this point by your geometric thing? So what you do is simply you will really use your little bit of geometric insight. So this is my point say 0. So you take this antipodal point minus xa, and if you go along the direction P some distance, then you will reach at SPX. So you have to really calculate that distance SPX. So this distance you need to calculate. So what
Muna,
you do?
could you repeat what you have just said?
So do you agree that SPX will be this point?
Yeah.
Because SP is the geodesic inversion, so SPX
Yeah.
is the thing. So I am saying that you have to really use your little bit of geometry, school geometry, to find this point SPX. What you take this X, and there is an antipodal point minus X. Okay, so if you go some distance along this, if it is okay, so you have to do it from geometry, right? So if minus X, you will go in the direction of P some distance, you will reach SPX. Okay, so you have to calculate that distance. Okay. So that distance will be somehow, you have to really draw this triangle like this, and this is my something like this distance. This distance is really which I am this is really X dot. Okay, so if you draw this triangle, and this distance will be X dot P, and this distance will be really X dot P. So total distance is 2 times X dot P. Okay. So that will be SPX will be minus X plus, okay, I will go some distance, I write this 2 X dot P, X dot P, and in the direction of P. So SPX will be this one. So from geometry you will get. Okay. So is it clear, Manoj?
Yeah, not fully, but okay.
Not
Carry
fully
on.
wide. See the
Carry
thing. You see this is clear from picture, right?
on. Yeah.
What is the confusion? Oh,
Minus
you are.
x plus this distance, and then
This is my
why
SPX.
I'm just confused. Why are you multiplying by p? It's maybe obvious,
No, I am
but
not
okay.
multiplying. What is
You're
this
taking
distance? This
2
is
times inner
x
product of
dot
x.
p.
Yes, that is x dot p times p.
This distance is x dot p. So this distance is parallel to this thing.
Yes.
So this will be same distance actually. X dot p.
Okay, okay. That's why you're taking p times this, right?
X dot p. This is not multiplication. X dot p.
That is x dot p, and then you're taking p, the vector p, right?
Because I am moving in the direction of p.
Yeah, yeah.
I am minus x and I am traveling 2 times x dot p, and so therefore I am getting this.
Yeah.
It is fully clear now.
Yes, yes, yes. Thank you.
Okay, so SPX is this thing. So is there anybody? Tapen, is it clear? Hello, Riju? Nobody is there, I think. Okay. Okay, so SPX is this thing. Okay, SPX is a map from Sn minus n to Sn minus 1, but you can really extend this SPX, okay, to a map from Rn to Rn, and this is the same map. We extend SP from really Rn to Rn by SP of V really minus V plus 2 into V plus P. Okay, this is the same map. Okay, and check that SP is a linear map. SP is linear map. Now, what is really SP of P? Okay. SP of P is really uh, minus P plus 2 times PP, and PP is 1, so this is minus P plus 2P, this is P. Okay, since P is now, as SP is linear, so I told you that, yes, as SP is linear, DSPP is really is equal to SP. Now, if V belongs to really TP of S minus 1, so what is DSP P is equal to minus V plus 2 into Vp and P. So, since V belongs to TPS minus 1, so this is really 0. Okay, as V belongs to TPS minus 1, this Vp is 0. So DSPB is equal to minus P, hence DSPP is really minus identity on TPS minus 1. Okay, so this is the thing now. So I have to really show that SP is in a isometry. So for that SPV, take SPW. So that is really minus B plus 2 VPP and minus W plus 2 WP is really VW. Okay. So I am doing this thing first. Sorry. I'm doing. So I am really taking this thing, my BW minus of 2 VP WP, and this is minus of, then second thing, minus of 2 VP WP.
So VW, are you taking in the tangent space or what?
No, BW belongs to Rn.
Rn. Okay. So you are showing that it's an isometry of Rn. Sorry.
No, I
Or
am
preserve the
saying,
Rn inner product. That's what you are showing.
yeah,
You automatically in ON.
ON, and this is PP square. This is real. Because this you can do this PP square is 1, so this is VW. So that means this implies really SP belongs to 1. Okay. So from here actually you can conclude that really SP we have calculated that shown that isometry of Sn minus 1 is OM, and from here actually you are really conclude this thing that SP belongs to isometry of Sn minus 1. But since this is a simpler example, it does not. I will not suggest that to really use that knowledge of isometry group. My point is just it can be also done without the knowledge of isometry group. So for this, just show. I will just show this once. Okay. So other things actually I will leave it. So you can
I didn't get you what you were saying about isometry group.
see the thing is, you know this isometry of Sn minus 1 ON.
Yes.
From there you can conclude that SP belongs to isometry of Sn minus 1, right?
Mm.
But I am saying that without using this knowledge, okay, can you show that SP in isometry of Sn minus 1? That is the thing. And I am saying that it is not good to use this thing. I'm saying this fact. Okay, you can show directly this thing,
Okay.
and I will show
And
it
you are
one.
also using the fact that this isometry group acts transitively, right?
Where I am not. I have not used anything.
No, but you are saying that these are symmetric spaces, or you are just showing that there exists one point,
Every point, this P is in any fixed point, and
any fixed
you
point.
so any P I am getting an isometry. Then
Okay.
obviously I am getting for other points also.
Other points also, yeah.
I am not using that proposition actually. I am just showing this is an yeah.
Okay.
So this is really SP from ON to ON is a diffeomorphism. Is a diffeomorphism.
These things are called transvection.
No sir, no. This will
Slightly.
not be.
Eh?
This will not be transvection. We will come to this. This is just geodesic inversion at the point P.
Right.
So
far,
that is different transversion. I will come to it. This is not a transvection actually.
no, only because you want to minus identity, the derivative, you are taking minus plus. You see, if you take V minus 2 VP, instead of minus V plus 2 VPP, that is the transfer.
That may be the case, but
Yeah. Here you are, because you want the derivative to be minus identity, you are taking. When you do SPNR, you will perhaps, I don't.
okay. So this is really SP from ON to ON is a diffeomorphism. So let
You are
you
showing
do.
this or what?
Oh my God, you are
Wow.
getting confused from from the first example. I am not doing anything. I want to show
No,
that
no.
SP.
What is your SP is a map from Sn minus 1 to Sn minus 1, right?
SP is an orthogonal map. Okay,
Yes,
I
SP
am just.
belongs to ON. Then you suddenly saying that SP from ON to
I
ON
want to
is.
show that SP is an isometry. Okay, I am doing that.
No, you have to do it over Sn minus 1. Now what he wants is correct.
So SP is an isometry of Sn minus 1.
But you have written SP is a mapping from ON to ON.
Oh, Sn minus 1 to Sn minus. Sorry. I. Oh God. SP and Sn minus 1 to Sn minus is a different method. Sorry. Okay, so let UB belongs to PQ Sn minus 1. So what I have to do, this is the matrix on the sphere. So G of AQ, DSP of Q, DSP of QB. So this is really DSP of QU, DSP QB. Yeah, so this is really U. DSP is the linear map. So DSPQ is really SP. And this is simply UB. And this is simply a GQ, QB. Okay. So that means this precisely means that SP star G. Hello? Mithunda,
Yes,
is it
Muna. Yeah, it's audible.
SP star G is equal to G? Okay, so this means that SP belongs to this I of Sn minus 1. So hence we get this, that we get Sn minus 1 is a RSS. So this was the thing, and I have to give two remarks. Remark first one, that from star previous star of the hello.
Yes, Muna.
Yes, we can hear you.
Okay, from star of previous, actually there was power cut here, so I do not know how is this from star of. You can hear me.
Yes, we can hear you. Please go ahead.
From star of previous page, and using the fact that I of Sn minus 1 is equal to On, one can also see that SP belongs to this ISN minus 1. Okay, so this is the thing. Second thing, actually I want to say that in let, so yeah, let so if M is an RSS, then SP can have more than one fixed point. So SP can have more than one fixed point. And hello?
Yes, Mona, I can hear you.
Yes, okay. So SP can have more than one fixed point. And for instance, if in case of Sn minus 1, so you really see that if you take the geodesic inverse on SP, there are two fixed points, P and minus P. Okay. So in case of Sn minus 1, we have P and minus P are fixed points of Sn. So I am hearing my echo. I don't know. Something happened. Sorry, actually, there was a power cut. So SP of minus P. So SP of V is really minus B plus to VP and P. So SP of minus P will be P plus 2 into minus P, P and P, and this will be really, if you calculate that, then you will get minus P. So it may happen that in involution there are more than one fixed points. Okay. So exercise, so that in Sn minus 1, so that P and minus P are the only fixed points of SP. Okay. So now actually I want to really do I want to prove again this Sn minus 1 is Riemannian symmetric space using another way, and that is also important thing. So, but that argument we will use this knowledge of so-called isometric group. Okay. So this another way I have to really please pay attention there. This is a very interesting.
Munada,
Yes.
so for compact case, we can see there can be example of many fixed points. Let's say for Sn minus 1. For non-compact case, is that possible? Means what I want to say that for non-compact case, will this be fixed point will be unique?
I am not sure at this point, but the thing is non-part that I am guessing that it will be the case, because probably I am not sure at this point. Okay.
Okay.
So I will tell you definitely. This is the question I will tell you.
Okay.
So another method. Actually, I think somebody has really not muted. He's really. I mean, somebody has to mute. Actually, I am seeing some. I am listening some sound there. Okay, now it is. I think it seems fine. So another method. So you have to use this fact that I of Sn minus 1 is really On. Yeah. Okay. So using this, we can really show also that sphere is a symmetric sphere. Okay, what I have to do? So let P belongs to really Sn minus 1. Okay. What? Let P belongs to Sn minus 1. I have to specify this SP. Okay. Now I have really have this thing SP of, I have two information in my thing. If I want to define SP, SPP has to P, and DSP P really has to be minus identity on the tangent space of Sn minus 1. Now what I will do, I will write this Rn plus 1 as two things, Rp plus direct sum of Rp perf. And what is Rp perf? Rp perf is really your TPSN minus 1. Okay. So now I have to specify this SP. Okay, SP is really what we are using this thing that SP.
Muna, what is RP?
RP the span of P, R into P.
Okay.
This vector RP, span of P. RP perf is TPS minus 1. Okay. So I have to specify this SP, but I already know that SP will be an linear map. So, but also on RP, since SP fixes P, on RP, SP will be identity. Okay. Now, since
Muna, I think we lost you. I cannot hear.
I can hear you.
is all. Okay, so what is in? Hello, Mitunda?
Yeah. Now I can hear you.
Okay, SP. Okay, SP is identity on RP. Do you agree with this? Do you agree this point that SP will be identity on RP?
Yes, Muna.
You agree with that because SP simply S will be linear map. So SP since fixed P, so S will fix RP. So SP will be identity on this thing, and DSPP on RP perp. RP perp is the tangent space. This is on the RP, but linear map. SP is multiple RP.
Your voice is breaking, Muna.
Okay. So just wait 1 minute, 1 or 2. I will get HRI connection. Actually, sorry because this is terrible problem. Okay, so now let me explain once more. See, SP is a. I have to specify SP. SP is a linear map. Okay, so what I know that on RP SP has to be identity. Okay, and on RP perp I know that DSPP is equal to really minus identity. Okay, so but DSPP is your SP. So SP is minus identity on RP perp. So SP on Rn plus 1. Oh, sorry, not Rn plus 1. This is Rn. SP on Rn is really, this is SP at identity on RP. And this is identity on minus identity on RP perp. And this is really specify the symmetry at the point P. And by definition, SP is an orthogonal map. So SP belongs to really IISc minus 1. Okay. This point itself proves that if somebody writes this line, SP on Rn is something like identity of RP plus minus identity on RP perp, then he is also saying that this Sn minus 1 is a Riemannian symmetric space. Okay. So I want to nail down it further. I want to calculate what is SP. So for that,
Muna, just could you repeat your last 2 sentences again?
what I'm saying, if somebody writes this line, SP on Rn is equal to identity of RP plus minus identity of RP plus, so then he is specifying the geodesic inversion at the point P. Okay.
No.
Because
Okay, so on the tangent space, this is minus identity.
yeah,
That's all you need, right?
Yeah, that's all you need to specify SP, right? Because SP is a linear map. So, and since this tangent space, it takes identity to minus identity, and on RP it is identity. It is clearly an orthogonal map. Clearly, SP belongs to ON, and this is really isometric of SN.
Munada, could you mention that how do you start? What you are aiming to do? Where we want to.
Yes.
You started with SP. SP is a linear map.
No. I have this. I have to find out SP. Okay.
Yeah. Okay.
So I have to find out SP. I have to define SP, right?
Okay.
But I have to define an SP in such a way that SPP should be P. Okay. On the tangent space, it should be minus identity. Okay.
Okay.
So I have to use this information. Okay.
Okay.
To specify SP. Now what I do, I decompose Rn in two forms. Okay, RP and RP form.
Okay.
I have that also one information in my mind. SP is a linear map.
Where do you get that information?
I told you that I have in this method I have to use this that I of Sn minus 1 is O, which I know already.
Okay.
I am using that thing. Okay.
Okay.
Now since I have to specify this SP on RP, since SP P is equal to P on RP, SP has to be identity.
Yeah. Yeah. Okay.
And on RP per DSPP is equal to minus identity. And since SP is linear, so DSP is P is equal to SP. So on RP per SP is minus identity. So SP on Rn is equal to identity of RP plus minus identity of RP per. Is this clear?
Yes, Munna. Thank you.
Now since SP belongs to N, this is the isometry. If you want to find the isometry, this is also easy. You just decompose, let B belongs to Rn. So decompose B is really like this, BP, P, and plus B minus BP, P, and this, okay, this BPP belongs to where? RP, and this belongs to really RP per. Or so that means SPB is really SPB will be, it will fix this BPP directs BPP, and second thing it will take minus. So this will be minus okay, B minus BP, and this is same thing as minus B plus 2 BP. So in this case also I am getting the isometry. Okay. So if you, so what it does basically, if you any vector B, you have to decompose into things. One is in the direction of P, and then in the direction of P per, and then in the direction of P we have to fix that component, and then the direction of RP per you have to just change that component to minus P. So this is at all. So if you really also in this setup also, if you draw the picture, so this is my say origin, and this is my P. Set. This is my point P, and this my X. So you have to decompose this into two components. This is really, this is my component in the P direction, and this is my component in the P per direction, and I have to only just take negative in the P per direction. So this is my negative, and this is my SPS. So in this case also you will get the same point. That is my point. Okay, so this is. I hope these things are clear to you. Is there anybody who couldn't understand this thing? No way, is it clear?
Yeah, it's clear.
So we want to get now the real hyperbolic space. The real hyperbolic space, the thing is, okay, it's already 420. Okay, real hyperbolic space. In the sphere case, we sort of know the geodesic, so that's why we could do it. But here actually this space is unfamiliar to all of us. So we at present we do not know what are the geodesic. So what we do, let P belongs to X, we will first make a lucky guess. Okay, so then hope that that will work. So SPX is really in the sphere case, this was the condition. SPX is equal to 2XPP. This was in the isometry in the sphere case. Now what you will do, you will just change this XP to some, okay, to this bilinear product. So Now hope this is what, but this SPP, if you will write that minus P plus 2 P and minus P, PP is minus 1, this minus 2P, this minus 3P. So this doesn't work really. But if you really modify that little bit, then it will work. So plus thing you really change to minus. That's all. It will work. So now SP extends to a linear map from Rn plus 1 to Rn plus 1. So first you check that SP of P is minus P minus up to PP P, and since PP is minus 1, this thing is minus 1, this is minus 1. Okay, so PP is minus 1. Use that part here. So this is minus P plus 2P, and this is P. Now if V belongs to TPHN, so this is SP DSPPV, as SP is linear map. So this is really SP of P, and this is minus P plus 2 PV, and this is since P belongs to TP, V belongs to TPHN, this will be 0. So this will be minus P, SP. So DSPV is minus. So this is DSP is really minus identity. Now what I am getting, DSPP minus identity, what I have to show? Okay, I have to show that SP belongs to so-called isometry of HN. So for that SP of P, okay, I am leaving this thing. Check that. So SP of V, SP of W is equal to VW. You just check that, and for all VW belongs to Rn plus 1. Now from here, actually this is an exercise, and this is easy to, from here we get that SP belongs to really ON1. So, and we have some information like this. I have discussed this thing, ON1 HN really HN, and O plus, okay, O minus plus N1, HN is equal to HN, and O plus minus N1, HN is equal to HN tilde, O minus plus N1 HN is equal to HN tilde. So I have this information with me. So since SP P is equal to
Another
P
on second, I think one for minus minus n.
Sorry, thanks. So last line, right? So this belongs to HN. So this implies SP belongs to where? O plus plus N1 disjoint union O minus plus N1, and this is really isometry of HN. So SP belongs to isometry of HN. So we have proved thus HN is a Riemannian symmetric space. Okay. So you can actually, as I told, that it is not really good to use this knowledge of isometric group. So one can also directly verify that, and I am giving you that exercise. Okay. So directly, without using, actually I have in the sphere case I have done it. In the HN case you have to do it without using the fact I of HN is really plus N1. descending to that SP belongs to IISc. So one may not need the knowledge of so-called isometric group to this. Now, as mathematicians, we do not really like so-called lucky guess, which I did here. We want to, therefore we will do this thing in the other method, which I described for sphere. Let us see how we will get this involution naturally. This symmetry I will get very clearly in that case without using so-called lucky guess. I am unable to write it. Another. So, and here, as I said, that I have to really use this fact that IHN is this O plus plus N1, this union O. I have to use this thing. So, what I will do, let P belongs to Hn. So I can decompose Rn plus 1 is really in this form Rp plus direct sum. This is Rp perp, and this perp is with respect to this bilinear perp. So, like the previous case, he is here, and what is Rp perp? Rp perp here is really TPHn. Like the previous case, I will get here SP is really identity here. On Rp perp, I will get SP is equal to DSP. P is really minus identity. Now, so SP on Rn plus 1. This is really identity on Rp plus minus identity on Rp perp. So that so let V belongs to really Rn plus 1. So I want to find this thing. Okay, SPV. So V can be written as alpha V plus W, where alpha P plus W, not where PW is 0. So suppose I am able to find this thing. So now if I take V, P, this is really alpha PP plus WP. I will use this part. So minus alpha, and this is 0. So alpha will be I will get minus of Vp. So that decomposition is B really got. So decomposition is minus Vp, okay, plus P plus Vp P, right, plus V minus P plus Vp. So now what will be SPV? So SPV will be, so first thing is belongs to Rp, and this is really belongs to Rp prop. And perp P perpendicular with respect to this bilinear one. SPB will be minus of Vp minus of VPP, and second thing is minus of V. Second thing will be minus, and this is same thing as minus VP, so minus of 2. So in this both cases, I am getting the same isometry. So now you can conclude that SP belongs to IHN. Okay, so we have seen that I will conclude after this point SP belongs to IHN. So hence we get that HN is a RSS. HN is RSS. So Tapendra, is it clear?
Yes, ma'am.
So now we will move to something. Okay, so some fact I have to really mention, some little bit of Lie theory. So fact. So let G be a Lie group and H be a closed subgroup of G. Okay, so let G be a Lie group and H be a closed subgroup of G. Okay, then G by H equipped with a so-called quotient topology. Topology can be made a smooth manifold. Made a manifold of dimension okay. Dimension equals to dimension of G minus dimension of H, so that the canonical projection map is smooth. Map P from G to G by H is smooth. Okay, so and another thing, so it says simply say that if G is a smooth Lie group and H is a closed subgroup of G, you look at the homogeneous space G by H, that is a smooth manifold, and it has dimension of G minus dimension of H, and that projection map is smooth. Okay, look at this in this thing. Look at this setup in the continuous case. Actually, if G by H is equipped with quotient topology, space of continuous functions on G by H to a some other continuous other topological space can be identified with right H invariant continuous function on G. Okay. So this also holds true in this case. So moreover, any smooth function from G by H to any to a smooth manifold, any superposition function f from G by H to a smooth manifold M can be identified the right H invariant smooth function f tilde from G to M in a canonical way. So this is, you have seen this thing in the continuous category, and this is say that in the smooth category also this is true. Okay, so now the thing is actually this is useful in this is a very useful fact. For instance, there will be certain spaces where you do not really know how to make those spaces a smooth manifold. But if you have a group action, then you can really make that space a smooth manifold using this fact. Okay, so let us do that one example. So, and that space we will show that the next class thing, that is a symmetric space. So this is called GKRN. So this is a real Grassmanian of K planes in Rn. Okay, and I have to here take 1 less than K less than N. And by definition, GKRN is something like B. So B is a subspace of subspace of P is a k-dimensional subspace of R. So this is the thing. Now orthogonal group acts on GKRN defined by this A dot B is equal to AB, where A is the image of B under the map. Okay. Here I am taking A belongs to N and B belongs to GKRN. So okay, so this is the this defines a group action. You can check that. Now, since SON is a subgroup of ON, SON also acts on GKRN. Now claim. So SON acts transitively on GKRN. So, and how to prove that? So let V comma W belongs to GKRN. This B is a WR is both V and W are k-dimensional subspace of Rn. Choose an orthonormal basis. Choose orthonormal basis V1, V2, Vk and Vk plus 1 Vn and W1, W2, Wk, Wk plus 1 Wn of Rn, so that this V1, V2, Vk, this belongs to V, and so and this W1, W2, Wk, and this belongs to W. So this is possible. Okay, so what I do, just choose a orthonormal basis V1, V2, Vk from B and extends to that an orthonormal basis of Rn, and similarly choose W1, W2, Wk is an orthonormal basis of W and extend to a external basis of Rn. That's all. So let T of Vi is equal to Wi 1 less than equal to I. So since T takes orthonormal basis to orthonormal basis, this implies T belongs to. Now, if necessary, by changing Wn to minus Wn, we can assume that determinant of T is really 1. That implies T belongs to S1. So this shows that hence SON. So SON, this shows that SON acts transitively on GKRN, but SON is a subgroup of ON. So and SON, this implies SON and ON both acts transitively on GKRN. Okay, so let E naught is equal to really span of this. Okay, let E is equal to span of this something like E1, E2, EK. This first K vectors. Now I will look at this H of. Okay, so let H of SON. This is really stabilizer of E inside the group SON, and let this thing H of ON is really stabilizer of E inside the group ON. So now, so let us use a phrase space. Okay, so let us see. Let A belongs to really this H of SOM. So A fixes this set, this vector space E. Now, if you look at this, what is AE1? Okay, so let us look at this. Okay, this suppose A is of this one. So AE1 you will be will by definition will be belong to E, because A fixes the set because fixes the space E. AU1 is the sum of linear sum of first kth basis vector, sum A1k ek. Sorry, A1k A no, let me write this. AU1 is something like I is equal to 1 to k A1 I say EI. So that means if you really look at the first column of A, so there will be something up to this kth row, and rest are the thing as 0. And similar thing will happen for this E2 also, and this will happen up to this kth column. Okay, so this will be 0 and there will be something. Now similarly you can prove that this will be 0 and there will be something here, star star star. Okay, so what I am saying that A will be of this form, like A will be of this form, from B 0 0 C, where B is this is a K cross K matrix and C is a n minus K cross n minus K matrix. So let us write that proof. So let us write that proof. I have explained this thing, but we have to write this. So let A is equal to A I is A. Okay. So I is equal to 1 to K EI. So now fix J greater than equal to K plus 1 first. So and suppose I and I fix this 1 less than equal to I less than equal to K. Fix J and I. Okay. So what is this? A is A of EI. This is really as A is orthogonal. So E is A. This will be AEI. Okay. A in A transpose EI. Sorry. Okay. So A transpose EI is the same thing as E is A inverse EI. Now since so this will be, since this A inverse this stabilizer is a group, so A inverse will be also H of SON, right? Because it is a group. So that means A inverse EI will be something like M is equal to 1 to K A of MI and EI. But J is greater than equal to K plus 1. So that will be, this will be 0. Okay. So hence A is of the form some B 0 0 C, where B is a K cross K matrix, B is equal to M K and C belongs to M n minus K. Now I know that this is really Rajesh Bhaiya, sorry, I am taking. I will just finish this. Okay. So since the A is an orthogonal matrix, so since A belongs to really ON, this implies B belongs to really SON. Now B belongs to really ON and C belongs to ON, and determinant of B into determinant of C is equal to 1, because this is determinant 1. So that means H of SON really is contained inside something we have. Hello? Is contained
Yes,
inside.
Muna.
Okay, I will just finish this thing, then we will stop. Okay.
Okay, okay.
So I'm sorry. Will I stop here or
Yeah, you
just
continue.
I will finish this thing? Okay. S of OK cross ON minus K, and other direction is easy to see that. It is also easy to see that. Easy to see that this is S of OK cross ON minus K is contained inside this H of SON. Hence, I'll get this H of SON really S of OK and O of n minus K. Okay. Now, similarly, the same argument actually usually say that H of ON will be what? So let me write that. The previous argument also shows that so H of ON is really OK cross ON minus K. Okay, because I don't have this condition on the determinant. So this is the thing. So hence we get that. Hence we get this GKRN. In one hand, I will get this ON mod OK cross ON minus K, and this is really SON mod this S of OK. So, let us write this not equal to this is something else. This is identity set theoretically. This is not very thing. So call the first thing is 1 and call the second thing is 1, right? Now, if you look at the 1, right hand side of 1, this I state that ON is a Lie group and OK cross ON minus K is a closed subgroup of ON. Therefore, the right hand side has a manifold structure. So using either 1 or 2, this origin 2, so one can define a topology and smooth structure on this topology and smooth structure on GKRN. Sorry, on GKRN. Okay. Now one can ask question. Suppose one gives a differentiable structure using 1 and one gives differentiable structure using 2. Are they same or different? They are in fact diffeomorphic. So both structure obtained. So one can show that uh, the, the structures, the smooth structure on GKRN obtained by 1 and 2 are diffeomorphic. Okay, so now the thing is from this condition 2. Okay, so observation from I am on observation. This is say from condition 2, since SON is really compact and connected, so GKRN is really connected. Observation. This first one is GKRN is compact and connected smooth manifold. So and there is some symmetry on this K and N minus K. So GKRN really diffeomorphic to Gn minus KRN, and this is diffeomorphism. because there is a symmetry in K and minus K. And third thing is G1 Rn. This is your Rpn minus 1. And this is, you know that this is a real projective space of dimension n minus 1. And fourth thing is really dimension of GKRN. You can verify that this is really K into n minus K. So with this, I would like to stop, and I will not. Okay, if there is question, you can ask quickly, or I will not take any question today as Rajesh Bhaiya has to go. Okay, is it clear or? Hello, Rajesh Bhaiya, will you stop?
Okay, yeah, you can, yeah.
Sorry,
So I'm stopping the recording.
yeah.
Thanks, Muna.
If they,
Yeah, thank you, Muna. Yeah, sure.
you can disconnect. If anybody wants to ask, he can ask question. But recording will not be there. Is there any question from anybody?